Okay, good morning, everyone. Welcome to Evolutionary Robotics. I'm the instructor for this course, Josh Bongard. We're going to spend a little bit of time this morning going over logistics, how this course is run. We're going to go very quickly through the syllabus, schedule, Brightspace. We'll get all the boring stuff out of the way, and then we'll deal with robots. Fair? Okay, logistics. There is one unofficial name for this course, Evolutionary Robotics, and there are several official names for this course, just to make sure that you're extra confused. Okay, first of all, for those of you that are taking this class for undergraduate credit, hopefully you are enrolled in CS 3060, and there is an associated Brightspace page for 3060. Everyone made their way more or less to Brightspace. You all know how to work Brightspace at this point. All good? Okay. All right. So the majority of you sitting in the room this morning, speaking of the room, there are 60 folks enrolled, and there should be 60 chairs in here. I think we're pretty good. Okay. For the majority of you taking this course, the majority of those of you taking this course are undergraduates. There is a minority of students in the class that are taking the class for graduate credit. If you are taking it for graduate credit, hopefully you are enrolled in CS 5060, CSIS 5990, or BME 990. Do those numbers sound familiar to the grad students? I see people nodding their heads. Okay, all right. Again, just to make sure you're extra confused, there are two Brightspace landing pages for this course. CS 3060, not problematic. If you're an undergrad, make sure that you're enrolled in 3060 through Brightspace. The name of the course for grad students in Brightspace is CSIS 590. Why CSIS 590 and what not CS 5060 or BME 590? I have absolutely no idea. There we go. Good? Brightspace? Okay, awesome. All right. If you are confused, hopefully, now you're unconfused, and find your way to Brightspace. I've linked the schedule and the syllabus. If you're not sure what's happening in the course, if you're not sure where we've just been, where we are, and where we're going, you should be able to find answers on Brightspace. There's the syllabus, there's the schedule, announcements. You already have an assignment assigned, which I'll talk about later this morning. Any questions at this point? Hopefully not. So far, so good? Okay, so again, there's a mixture of undergrads and grads in this course, and I'm going to talk about how that's sort of administered in a moment. So there are two separate syllabi, one syllabus for the undergrads, one syllabus for the grad students, and we all share one single schedule, which I will refer to at the beginning of each class to, again, keep you oriented for where we are, where we've been, where we are, and where we're going. For those sitting in the back row, can you read that? Or do you need it larger? Shake your head no if you can't. All good? Okay, all right. Okay, so we're going to very quickly go through the syllabus. Obviously, you could sit down and read the syllabus, but I just want to make sure that we're all literally and figuratively on the same page. Okay, you've all found your way here, so you know that we meet in Innovation E430 at 8:30 in the morning. Why the heck do we have a class at 8:30 in the morning? The reason is that I'm a morning person and I always request morning classes. So when you're cursing the fact that you got to get up early for this class, I'm the reason, just so you know. Okay. All right, we're here Tuesdays and Thursdays, just to make sure you can always find the schedule and the syllabus. They link to each other. Okay. Again, I'm the instructor. I'm pretty informal. You can call me Josh. That's perfectly fine. There's my email. If you click on this link here, it'll take you to a spreadsheet that explains how to make my office hours. I'm happy to meet with you in person or virtually. It's all explained behind that link. If you find that you want to meet with me and you can't make any of my office hours, shoot me an email and we can usually arrange a time to meet. Okay. Anna Rees is the teaching assistant for this class. Anna, can you hold up your hand? Anna took this class last year and did very well. Congratulations. So she's being punished for her good works by being invited back to be the teaching assistant for this course. There's Anna's email, and Anna also has a spreadsheet that explains how to meet with her either in person or remotely. Okay. Okay, UVM requires me to try and boil this course down into a soundbite for you, so here's my best attempt. This gives you, I hope, a 10,000-foot view about what we're going to be doing in this course and what I hope you all get out of it. We're going to spend most of our time talking about the automated design of autonomous machines. First thing I want you to notice is that the word autonomy appears twice in the sentence. We're going to be focused, as the name of the course implies, on robots. These are autonomous robots, not remote-controlled drones. There is no human that is controlling the machine. The moment we start talking about those kinds of robots, things get very interesting and very scary very quickly. Tricky thing to make a machine that operates autonomously and acts on behalf of the human operator, program designer, society as a whole. Tricky thing to do, and I hope one of the things you take away from this course is how difficult it is to do, but I also hope you take away from this course why it's really, really, really worthwhile to try and do this. Okay. If you think an autonomous machine is difficult, or designing or creating or training an autonomous machine, in this course, we're going to focus on the automated design of autonomous machines. What does that mean? We're going to automatically design robots in this course, which means you're going to create AI, and that AI in turn is going to create robots on your behalf. So the AI is going to be autonomous in the sense that it's going to search over the space of all possible robots that could be built on your behalf, and it's going to try and find the good ones. Once it does, it's going to design them, and we're not going to manufacture any robots in this course, so we won't be bringing anything into reality. But in theory, the AI on your behalf is going to design an autonomous machine that does something useful or interesting on behalf of all of us. Okay, what is this AI? This AI is obviously a big catch-all term these days. We're going to focus on a particular type of AI known as an evolutionary algorithm. We'll get to evolutionary algorithms later. Okay, another thing you will notice about this course is it's very broad, not necessarily very deep. What do I mean by that? We're going to cover a lot of different subjects, some of which you may have never seen before, and we're going to dip into all of them deep enough to pull out all the pieces we need to cobble together to automatically design autonomous machines. You may find, and many students have in the past, found themselves being frustrated that we touch on a particular topic like biomechanics and we just scratch the surface. Every noun that's listed in this long laundry list here, there's a whole course. There could be a couple courses for some of these topics. We might spend one lecture talking about it. We might spend 10 minutes talking about it. So I invite you in this broad sort of survey course, when you stumble across a topic that you're interested in, take the initiative and dig a little deeper. Okay, so we're going to talk about lots of different things. We're going to talk about AI in general and evolutionary computation in particular, which is the type of AI that's going to automatically design autonomous machines for us. These autonomous machines are going to be controlled. Their brain is going to take the form of an artificial neural network. Again, there's a whole course here at UVM about neural networks. Another course on machine learning. Professor Cheney teaches a whole course on evolutionary computation, which I highly recommend. We're going to talk about what exactly robots are, obviously. In order for most robots to be useful, they have to be motile or mobile. They need to move around. That's a big part of the definition of a robot. Getting from point A to point B, for us humans, feels effortless. We're really, really good at it. At least you are now. When you were 2 or 3 or 4, you were still maybe cutting your teeth on it. It feels like an easy thing to get around from point A to point B without bumping into things or running over humans. For machines, still a little bit tricky. So we're going to spend quite a bit of time dipping into all of the solutions that Mother Nature has come up with to get organisms from point A to point B and try and borrow some of those ideas for robotics. As I mentioned, this is not an engineering class. This is a computer science class, so we're not going to be building physical robots. We're going to be teaching AI to build robots for us in simulation. So if this pipeline isn't long enough already, you're going to create AI, which in turn is going to create robots in a physics engine and test out how well those robots work in a physics engine before deploying them out there in the real world where they may or may not do what we want them to do. So we're going to spend quite a bit of time talking about physical simulation. You're going to end up spending quite a bit of time working with a physics engine as part of the programming projects in this course. We will end this course talking about an entity that has lots of different names. One of them is computer-designed organism. The other name is biobot. The other name is xenobots. This is a discovery that came out of my lab in collaboration with Tufts about 5 years ago now. These are very, very small robots that are not made from metal and plastics and ceramics and batteries and sensors and motors. These are robots that are designed by an AI. They're computationally designed, but they're made from living cells. We'll get to the xenobots later. Okay. All right. So again, we're going to survey a lot of topics. In parallel to the lectures and the surveying of all relevant topics, you're going to spend a lot of time coding in this course. So you all will be conducting a major Python programming project that will span the length of the course and will give you hands-on experience with not all of the topics we cover, but hopefully most of them. Okay. It's going to take you the first 10 weeks of the course to do all of these programming projects. And then in the remaining 3 or 4 weeks of the class, you're going to use this code base you've developed as part of these programming projects to carry out your own experiment. You're going to ask the AI to design a robot for you that runs, that moves through a debris field, that collects items of interest from the surface of Mars, that navigates through the human body, that acts as a swarm. It's up to you. You'll get to choose. Okay. Any questions about the 10,000-foot view for the course? My apologies. I'm going to do most of the talking today. Hopefully things will be more interactive in later classes. Okay. All right. So again, what do I hope you get out of this class? The first thing is to gain an appreciation for and an ability to automatically design and simulate robot controllers. Standard approach in robotics is you manually make the robot body, and then you ask an AI to train the brain of that robot for you. You're going to hopefully become proficient in using robot simulation tools. Again, you're not going to be building any physical robots. And you're going to learn how to use simulation to test candidate robots. How well or how poorly do the robots do in a virtual world before we let them loose on reality. Okay. Hopefully you'll gain an appreciation for the limits and the challenges, and it should say here also the opportunities of robot simulation. Robotics is a massive field. There's a lot of different ways or a lot of different approaches to the creation of autonomous machines. In this course, we're going to look at a specific approach. Create an AI, get it to build a robot for you in simulation, and test it out before deploying it in the real world. I want you to understand the pros and cons of that, and we'll touch on other approaches in robotics, and hopefully you'll gain an appreciation for the pros and cons of those approaches. Okay. I hope you learn to evaluate and compare the performance of different kinds of robot designs and control strategies. What do I mean by designs and control strategies? In this course, we're going to look at lots and lots of different robots with lots of different kinds of bodies and brains. This is a very real challenge that all roboticists face. NASA is continuously considering the next generation of robot explorers they want to deploy into the solar system. Some of those designs are swimming machines, flying machines, crawling machines, walking machines. What's the right body for an autonomous machine when you're going to deploy it into an environment where you don't know a lot about that environment? By definition, the rest of the solar system. Tricky. You need to sort of weigh the pros and cons of body versus brain. Okay. You'll also gain familiarity with different evolutionary algorithms. Again, it's this particular flavor of AI that we're going to focus on in this class. Okay. That's learning outcomes, tools. Obviously, everything, good starting point for everything in the course is Brightspace. We use Microsoft Teams. If you want to contact me, you can email me, reach me through Teams, talk to me before or after class. Everything's fine. Okay. Obviously, you can also talk, you can get a hold of Anna, the TA, your fellow students in Teams. That goes without saying. Okay, in-person lectures. I am recording this lecture, and I will record all lectures, and I throw them up on YouTube after class. We will use Reddit for all the programming assignments. They are all embedded in a particular subreddit. So that subreddit sort of acts as an online course that shadows this in-person course. We'll talk more about the subreddit in a few minutes. Okay, Google Sheets for taking attendance. At the beginning of every class, I will throw up a link to the spreadsheet. So I invite you now, if you haven't already, get out your device, point it at this URL, and tick yourself as present for today. Hopefully you all have access to that spreadsheet. Yes, okay, good. Okay, see boxes being ticked? Great. Okay. All right, so you are using your devices now. You may use your devices today, but starting on Thursday moving forward, when lecture starts, I invite you to stow all your devices for class. Bit of a controversial decision. I invite you to go have a look at the literature. The literature seems to be converging on the consensus that students learn better when they pay attention in class to what's going on at the front of the room and mechanically or physically take notes as we go. Yeah? Okay. I've had a request. Some folks, question in the back.
Yeah. If we take notes on like an iPad but with a pencil, is that okay?
We will make an exception. If you like to take notes on a stylus or a tablet, that is okay, with one stipulation, which is please make sure it's lying flat on your desk. One of the things I've noticed is sometimes someone has some eye candy on their screen at the front of the class, which everyone behind them can see. Fair? Okay. Thank you. Any other questions about that? Okay. Okay, lectures. Obviously, lectures are here in person, as I've already mentioned. I record them live and I post them on YouTube right after class. I've got the mic on. It's obviously picking up my audio. If anyone in class asks a question, it usually shows up on the recording as mumble, 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 mumble. So you will remain anonymous. You can go back and have a look at recorded lectures from previous years, but know that if you do speak up in class, you are being recorded. I can guarantee you it will not de-anonymize you when I put it up on YouTube after the fact. Fair enough? Okay. All right. That being said, if you speak in class, you are tacitly agreeing to be audio recorded. Okay. Versions of these lecture slides, I'll post them online before class on the schedule. We'll switch to the schedule in a moment. It's just a Google slide deck. So again, there's various ways that you can take notes during class. You can either print out those slides beforehand and do it the old-fashioned way during lecture. Otherwise, you can come to class and just take pen and paper notes. You can always refer to the recording after class. Some students like to watch the lecture and then annotate electronically on the Google Slides after class. However you want to do it is fine. If you want to come to class and just sit quietly and listen and think, that's also perfectly fine. Okay. Those rules usually make it so that anyone who usually needs an accommodation for this class doesn't. If you still feel you need accommodation, no problem. Let me know and we can work something out. Yes?
Are there exams?
There is no final exam in this class. Which for most of you, that's all right. For most of you, that sounds like good news. but you might be wanting to think, what's the alternative? We'll get to what you're going to be doing at the end of this course instead of the final exam. We'll get there. Okay. All right. There is, I guess, a textbook for this class. It's hopelessly out of date. Anything to do with AI and robotics, if it's over a year old, it's kind of out of date. So I don't know whether textbooks even make sense anymore for anything to do with AI and robotics. That being said, there is sort of a satisfying benefit of a physical big thing printed on dead trees. So if you want one, there it is. That's the best thing. A lot of the concepts and ideas in this book are still relevant. A lot of the questions that are posed in this book remain unanswered. So I would say it is definitely still of value. The specific technologies and robots that are mentioned in the book, out of date. Okay. There is also a supplementary textbook for this class. I'm the co-author of this book. Thanks to the wonders of modern publishing. If for some reason you were inclined to buy this book, it costs about $40 on Amazon. The publisher gets $37. My PhD advisor, Rolf, gets $2. And I get $1. As I mentioned, there's 60 of you signed up for this class. So if I twist all your arms and convince you to buy the book, I'll be $60 richer. So it's up to you. Okay. As I mentioned, I don't know if it makes sense for there to be a textbook anymore for this course. Things are moving very quickly in AI and robotics. So most of the reading you're going to be assigned in this class are going to be PDFs from research papers and things that have happened in just the last few years. For most of you, hopefully, that makes things kind of exciting. This is not a calculus class. We're not going to be talking about things that were invented 300 years ago. We're going to be talking about things that were invented 30 years ago, 3 years ago, and 3 months ago. That can also be a little bit scary because one of the nice things about a textbook is obviously it's sort of pre-digested material that's spat back at you. For some of you, you're going to be doing a lot more reading of primary sources than you're comfortable with. You're going to be reading research papers with lots of technical jargon, lots of math in it. Don't panic. We'll work our way through that when we get there. All right? Okay. Let's see. Prerequisites for the course. Hopefully everybody here has junior standing and above. As I mentioned, there's a lot of coding in this class. So one of the prerequisites I set is programming experience. Some of you may be thinking at this point, do I have enough programming experience for this course? My answer to that thought is, I don't know. So the reason we assign assignment 1 today is so that hopefully for those of you that are not sure whether this course is right for you or whether you're ready for this course yet, I suggest you dive into assignment 1. That's going to get you coding up a physics engine immediately. Assignment 1 is due a week from now. So I would suggest you get started. If you find you're struggling with it and you're putting in tens of hours and you're starting to worry that you may not have it done by next week, that's usually a signal that this course is not yet right for you. If you dive in and it takes you 3-4 hours to make your way through assignment 1 and you find it fun and you get stuck at a few places, but other than that, it's relatively smooth sailing, then I would say this course is right for you. Yeah? If you're still not sure, come and see Anna and myself this first week. Show us how far you've gotten with assignment 1 and we'll try and help you make a determination whether this course is right for you or not. Yeah? Okay. On that topic, this course is currently fully prescribed. So if you find that this course is not right for you and you withdraw, we're sorry to see you go and we wish you the best. Please email me and let me know because there is a wait list for this course and we will let somebody else in who's currently waiting. Fair? Okay. All right. Grading scheme, late policy for this class. You're going to be submitting assignments, quizzes, a bunch of stuff. If you submit the material 1 day late, 25% deduction. If you submit stuff 2 days late, 50% deduction. If you find you're submitting materials 3 or more days, you can submit it if you want, but you don't necessarily have to for that reason. Fair? Okay. Just to make sure that you stay in sync with the course as we go. As I mentioned, this is pretty broad. We're going to touch on a lot of different topics. There's going to be a lot of coding. It's a bit like a math class. If you fall behind, it can be a little bit difficult. It can be a little bit difficult or a lot difficult, depending, to catch up. That's why the late policy is there. Okay. Letter, percent to letter grade, just so you know. There it is. Okay. All right, again, I'm doing all the talking. Any questions, comments? Anyone want to drop out now? You're still all here? Good. Okay. All right. Okay. The backbone of this course is not me talking at you. The backbone of this course is these 10 programming assignments. Each one takes 1 week. And so for the undergraduates, you will be done all 10 programming assignments in 10 weeks from now, and it'll eat up 40% of your grade. Yeah. We always assign the current week's assignment now, Tuesday morning, and it is due 11:59 p.m. next Monday. So next Monday at 11:59 p.m., make sure you've submitted assignment 1. And then the following morning, Tuesday morning, I will talk a little bit about assignment 2, and off we go. Okay. All right. These weekly programming projects are cumulative. They build on the one from the week before. So if you don't finish the current week's one and you're assigned the next one, you can't even start on that week's one until you finish the one from the week before. That's why it's like a math class. Actually, it's more like a math class. Things are more cumulative here than in most of the classes you've taken before. I'm sorry I'm repeating myself. I just want to make it crystal clear. Try not to fall behind. If you find that you are, the best thing you can do is come and see Anna and myself. If you're proactive and you let us know when you're starting to fall behind, not weeks and weeks after, we can usually get you dug out of your hole. But if you leave it too long, it gets increasingly hard for us to find solutions for you. Okay. All right. So what are you going to be doing during these 10 weeks? You're going to be gradually building a software system that allows you to conduct an evolutionary robotics experiment. You're going to be building a physics engine in the first few weeks. Then you're going to be building an AI system that you're going to wrap around this physics engine. And the AI is going to evolve populations of virtual robots inside that physics engine. So at the end of these 10 weeks, you're going to have something like that's going to look a lot like Russian nesting dolls. On the outer surface, you're going to have this AI. Inside the AI is a physics engine. The AI is looking inside the physics engine and watching what happens. Inside the physics engine, you're going to have one or more virtual robots running around in this physics engine. And inside each robot is going to be an artificial neural network that's transforming that robot's incoming sensation into actions. Not unlike your brain takes sensory input and produces actions. AI, physics engine, virtual robots, artificial neural networks inside. That's what you'll have at the end of 10 weeks. Okay. Okay. In addition to the assignments, there are quizzes that are due at 11:59 p.m. of every lecture day. So that's a quiz that's due by 11:59 p.m. on Tuesdays and Thursdays. Okay. These multiple choice quizzes, there's an artifact from previous years. That should say Brightspace. So when I get back to my office is on the other side of this wall, so I'm not going far, I will post a quiz on Brightspace. If you've done the reading for today and you've just come fresh from lecture, you should probably be able to blast through the quiz in 5 or 10 minutes or less. The quizzes are meant to be a gentle but consistent prod to keep you on top of all of the lecture and reading materials for the course. Okay. Okay. Final project is worth 30% of your grade. So at the end of 10 weeks, you then have, I never know whether it's 3 or 4 weeks, whatever it is, you got 3 or 4 weeks at the end of the semester to finally not do what I tell you to do, but do something on your own. You can come up with whatever idea you like. You're going to alter the AI so it goes and designs a robot in simulation for you that does that thing that you're interested in. Over those 3 or 4 weeks, you will still be submitting a weekly deliverable every Monday night, like you did the previous 10 weeks, because I don't know about you, but I always leave things to the night before. You don't want to leave your final project to the night before. So you'll be submitting weekly deliverables that update Anna and myself on your progress. How are you doing towards the final goal of your final project? Okay. Those are the weekly deliverables. And then as I've already mentioned, there is no final exam in this course. Instead, at the end of the course, you will submit a written report describing the experiment that you conducted, and you will give an oral presentation during the 3-hour exam period that we have, which is in this class. There are 60 of you in this class. We have 3 hours, which means you're going to have 3 minutes to describe your final project. It's not a lot of time. For some of you, you're thinking, thank God, I don't have to do a 3-hour exam. All I need to do is talk for 3 minutes. Some of you are panicking for the opposite reason. You got to speak for 3 minutes rather than write quietly for 3 hours. Pros and cons. Okay. Any question about that? No? Okay. All right. Participation. You've just ticked yourself off as present. Seems like a kindergarten-y type thing to do. I've taught this class for several years now, and I find that folks that come to class or regularly keep on top of the recorded lecture, take the quizzes, those that stay on top of the material do well in this course. Those who stop coming to class and start missing a few quizzes and then start missing a lot of quizzes, surprise, surprise, they end up not doing so well at the end. So there's a 5% participation grade, which, like the quizzes, is a gentle but consistent prod to stay on top of all the material in this course. Okay. You're permitted to miss up to and including 3 classes. I don't expect perfect attendance without being required to provide justification. If you find that you're missing 4 or more classes, the moment you notice that, come and see Anna and myself, and again, we can usually accommodate you. We can find a solution. If you wake up one day and realize you've missed 9 classes and only then are you going to let the TA and I know, it's going to be harder for us to dig you out of that particular hole. Be proactive. Okay. Okay. So if you come to class, you know how we do things. I will put up a unique URL at the beginning of every class. Before I start talking or while I begin talking, get out your device, tick yourself off, stow your device again. Okay. If you can't make it to class, you need to go on vacation, you have a family member who's ill, you need to travel, you are ill and you can't come to class, you think you're ill and you don't want to get your fellow classmates ill as well, stay home. As I mentioned, I record the lectures, I throw them up on YouTube. They usually are live and available around noon. Tune in at noon. You can watch the recorded lecture. As you're watching the recorded lecture, at some point in that recording, a URL will pop up. When that URL pops up, go to that URL and tick yourself off as present. From my perspective, at the end of the day, I look at the attendance sheet and I can see who attended class either in person or at home, no problem. You don't need to clear all these exceptions with Anna and myself. Makes things easier for us and hopefully makes things easier for you. Fair? Reasonable? Understandable? Good. Okay. All right. I designed the system so it doesn't penalize you for attending remotely if you want. Okay. Any questions about any of that? Okay. So that was the undergraduate syllabus. I'm going to switch now to the graduate syllabus. Maybe. There we go. Okay. Looks exactly like the undergraduate one. I just want to highlight a few differences here. Let me skip ahead to assignments. Okay. Okay. Graduate students, you are going to be doing the 10 programming assignments that I just talked about, but you're going to do them double time. You're going to do assignments 1 and 2 this first week, assignments 3 and 4 in week 2, and so on. If you're really good at math, you'll be able to work out that means you'll be done 5 weeks from now. The graduate students will then start in on an additional 5 assignments that recapitulate the original 10 assignments, but you're going to use a different AI. In these 10 programming projects that I just told you about, you're going to be using an evolutionary algorithm, and that evolutionary algorithm is going to evolve robots for you. In the additional 5 assignments, you're going to do the same thing again. An AI is going to design a robot for you in simulation, but that AI is now going to be gradient descent, and it's going to use a differentiable physics engine. If those words mean nothing to you, that's perfectly fine. We'll get to those topics in a moment. Yeah? Okay. So for the graduate students, you're going to be doing these additional 5 assignments that combine gradient descent with a differentiable physics engine in weeks 6, 7, 8, 9, and 10, which means you will end at the same time as the undergrads. We'll all be done with programming assignments by the end of week 10, and then grad students, like the undergrads, you'll have 3 or 4 weeks to do a final project of your own design. Okay, I think everything else is the same. There's a little note here on page 1. So Anna, the teaching assistant, she will be grading all of the first 10 programming assignments, and the ones involving gradient descent and a differentiable physics engine, I will be grading them. If when you get to those additional 5 assignments, if you find yourself stuck or have questions, come and see me. Okay. Okay. Any questions about expectations for the course, how things run? All good? Okay, thank you for your patience. I promise you this is going to be the most boring part of the entire course. All right, so let's have a look at the schedule. I will put this up at the beginning. Of every class, just so we know where we are, where we've been, and where we're going. You will notice in the schedule, first of all, at the top, I've been recording lectures. I've been recording the lectures for this course since 2016. So if you're not tired of my voice by now, you can go and listen to me lecture in previous years if you like. Okay. The course is broken down into 1, 2, 3, 4, 5, 6, 7 different topics. Topic number 1, introduction. So why robots? What is a robot? We're going to talk about the why and the what. Why do we want to build robots and what are they? Theme number 2, the tools of the trade. This is the how. How do we go about building robots? As I mentioned, robotics is a massive field. We're going to look at how we evolve robots. There's a number of tools of the trade that we're going to have to learn and that you're going to be cobbling together in the first few of these programming assignments. Third theme of the course is the history of evolutionary robotics. Evolutionary robotics was invented in 1992. So what is that? This idea is 23 years old. Hasn't been around very long. It's a relatively new subject, which again, hopefully I think you'll find interesting. You'll find that as we go through this course, there's many more questions than answers. I'm hoping that some of you get interested in this topic and maybe years from now you come up with your own answers to some of these unanswered questions. So we'll breeze through the first 23 years of evolutionary robotics, and then in theme 4, we'll move on to locomotion. There's an old question in biology, which is, why don't trees have brains? Why don't trees have brains? Why don't plants have brains? Kind of giving you the answer here on because they don't move. Brains, Mother Nature invented brains for movement. That was their first and primary function. Everything else that brains do, including your brain, is either something that's been cobbled on top of locomotion, or your brain doesn't actually do it, but you think it does. We'll get into that a little bit later. So it seems kind of odd in an AI class to be talking about biomechanics and locomotion. Makes a little bit more sense in robotics. But the real reason we're going to talk about locomotion is that intelligence is required when you move around. If your solution to life is to stay put and hope that stuff comes to you, you don't really need a lot of intelligence, or at least not animal intelligence. I guess if plants could speak, they might have a different opinion on all of this. This is a little bit zoochauvinism here. We're animals, obviously we're intelligent, we're better than plants, we move around, we have big brains. Okay. Locomotion is at the heart of intelligence. This is obviously something already that's very different from most of AI. ChatGPT doesn't move around and doesn't seem to think that it needs to. regardless of whether you think ChatGPT is intelligent or not, it is a type of intelligence that does not derive from locomotion. Your intelligence does. So we're going to spend some time looking at the connections between locomotion and intelligence. As I mentioned, evolutionary robotics is a relatively new field. There's a lot of open problems, challenges in the field, things that we know are a huge, huge problem to making safe and useful autonomous machines that we haven't solved yet. If we'd solved them, they'd be here. They'd be out shoveling the snow today. The fact that there aren't any robots around is a very clear signal that there are open problems in robotics that no one has solved yet. Despite all the fancy videos on YouTube, robotics in general is an unsolved problem. It's an open frontier. Again, part of the reason why I run this course, it's a bit of an advertisement and a recruiting effort. I hope some of you come and join the cause and help us try and create autonomous and safe and useful machines in the years to come. So what are those open problems? We're going to spend quite a bit of time going through them. We'll have a short break in the middle of March. And then we'll move on to the fifth theme of the course, the sixth theme of the course, collective robotics. There are many things in this world that one human cannot do on their own, but if they incentivize their peers correctly, a group of humans can do. Same thing with machines and organisms, for that matter. Collective robotics and collective intelligence looks very different from individual intelligence, and we'll look at the similarities and differences. The seventh and final theme of the course is called Evolving Bodies and Brains. Standard approach in robotics is for a bunch of human engineers to build the body, and only then bring in AI to train the brain of the robot. That is, of course, not how Mother Nature operates. Mother Nature continuously tinkers with body plans and nervous systems, with bodies and brains, to find good combinations that allow that organism to survive and thrive and produce offspring in the difficult world that exists out there. So evolutionary robotics is a bit of a gamble. It's a bit of a bet that if we are eventually going to make safe and useful autonomous machines, the way we're going to do it is not by training their brains, but by evolving them, evolving both their bodies and brains. Okay, so here's the schedule. There's a total at the moment of 24 lectures, which gives us quite a bit of a gap towards the end of the semester. Some of these 24 lectures take more than 75 minutes, so I'll keep updating this course as we go, and I will probably start to fill up, we'll probably push a lot of these lectures back and fill up most of the course. If we have remaining time at the end, we'll have some open discussions about the ethics and morality of robotics. There's some other topics that I haven't managed to wedge into the course yet. I might bring them back onto the schedule. We'll see. We've got a little bit of time at the end of the course to play around with. Okay, so that's the sort of flow of the course. If you look across these columns, here's today, lecture 1. There is a slide deck for today, which I haven't yet got to, but I'm going to get to in about 3 minutes. There's a link to the slides for today. There is some required reading for today. I would suggest you do that required reading before tackling the quiz, or have the required reading open while you're taking the quiz. You're taking the quiz at home, so it's open book. And there's information in the remaining columns. So here is the assignment. Here's the column for the undergrads. So for undergrads, you have now been assigned assignment 1, which if we go back to Brightspace, there it is down there. You can click on it and find out what you need to do. And you can see that next Monday at 11:59 p.m., assignment 1 is due for the undergrads. For the grad students, you're being assigned assignments 1 and 2 for today. Grad students, you need to submit assignment 1 and 2 by 11:59 on Monday. When I get back to my office, one other thing I will do is add a link to this cell, bring up the slide deck for Thursday, and so on and so forth. Yeah? Okay, any questions about the schedule? No? Okay, thank you for your patience. Thank you for your patience. Okay. All right, we're going to start by talking about the why of robotics. We are going to spend a lot of time here, and you're going to spend a lot of time at home making robots. It's really hard. It can be very frustrating at times. Why are you all, and why are we as a society in general, putting all this time, money, and effort into making autonomous machines? I'm going to give you four of my reasons for why I've dedicated my professional life to trying to make robots. I hope you come up with some answers of your own. I forgot to mention, I work in evolutionary robotics. It's a recent field. It's also a pretty small field. Depending on how you count, there's 14 professors around the world that work on evolutionary robotics. I'm one of them. So I'm obviously hopelessly biased. I think this is the way to achieve autonomous and safe machines. This is a disclaimer. I should really put this on the syllabus. You don't necessarily need to agree with me. A lot of what you're going to hear in this class is opinion, and I want to hear your opinions on the pros and cons of different ways of creating machines, and even whether we should be doing this. You are entitled to your opinion. I encourage you to have an opinion. I encourage you to develop your opinion and make it clear in class. I'm pretty passionate about this subject. I'm going to really hammer home my ideas on why I think all of this is important. You don't necessarily need to agree with it. Okay. As I mentioned, I'm going to give you several reasons why we might want to create robots. The first reason is an existential reason. ChatGPT is always so polite. Can't do it. Seems like a ridiculous example. Unfortunately, as a global society, as you all know, we are facing some pretty serious, scary global challenges. For some of those challenges, we do not know what the solution is. As you all know, microplastics is a problem. Microplastics are everywhere, and they're increasing in concentration. They're in you. They're in my 3-year-old son. They're in places in your body you absolutely do not want to have microplastics. There is nothing at the moment that we know of that can go in and pull the microplastics out of waterways, the soil, pull those microplastics out of you. Yet, we don't. There are many other global challenges out there that we do know the solutions to, but they're either too hard to build, they're too expensive, the labor would be too expensive. If we had robots that could act usefully and safely on our behalf, and we could deploy enough of them, we could build a lot of infrastructure that would solve some of the major challenges that we face out there. Still can't do it quite yet. Again, we're having a problem building autonomous machines that are both safe and useful. But if we could, what kind of infrastructure might they be able to build that could help with some of the big problems that we're facing at the moment? Ideas? Let's make it more concrete. There is one particular problem that's on the front of the news at the moment.
California wildfires?
Wildfires. How are they being combated right now? What's happening in Los Angeles right now?
Firefighters, many of which are incarcerated.
Yes, firefighters, many of whom are incarcerated. They're also humans. Human firefighters are fighting wildfires. I'm sure you've seen the footage. Who or what else is also combating the wildfires, aside from the human firefighters on the ground?
The ones in the planes.
Sorry?
The ones in the planes.
The ones in the planes. The humans in the planes. What are those humans in those planes doing? I'm sure you've seen the footage. How? How are they combating the wildfires? They're dropping water that they get from flying a 120-ton machine at very high velocity, about 6 inches above a body of water, scooping up water, taking it back to the wildfire, and dumping it. There's a human being at the controls. Thank goodness for these people. But wouldn't it be nice if they had some help, or they were replaced by automated machines that could go in and do all this on our behalf? Again, we're already straying into very tricky moral and ethical territory. But from the point of view of those people that are literally at or near the flames right now, I would imagine they might benefit from a little bit of help. Yeah? Okay. A little bit of pathos this morning, but I really want to impress upon you the real world needs for this kind of technology, autonomous machines. We're going to spend 99.9% of the class talking about the how. What's the best way we currently know to try and create those machines? What do we still not understand? How can we improve the way we go about building autonomous and safe machines? There's a reason why, and one of those reasons, at least in my opinion, which you don't necessarily need to share, is an existential one. Okay, second reason is an economic reason. Tell me about these 4 photographs. There's something common among the top pair of images and something that's common between the bottom pair of images. What is it? What's the story that's being told in the top pair of images? Yes?
It's been the same for a while with how we do things, except in the top, it's like factory working humans, and now it's robots doing it. But then for construction, it's humans still doing it.
Humans still doing it in the way we were just talking about the firefighters. So top left is one of Henry Ford's very first factories. Henry Ford had the idea that if we wanted to build a large number of things, in this photo it happens to be motorcycles, instead of having one artisan build the entire thing, let's instead have specialized workers who only know how to build one part of the thing being built, and then move these specialized workers from bench to bench and add their little piece to the machine as they go. One of the big inventions around this idea of mass production was to systematize the way that we build things. All the benches should be the same height, should be easy for the humans to move from one bench to the next. When the human specialist arrives at bench I, they always find more or less the same thing, so they can easily add their piece to the growing machine. Henry Ford is known for a lot of things, but the real genius, in my opinion, was this idea of systematization and specialization. So Henry Ford, through the idea of mass production, systematized the way that we in the West build large numbers of things indoors. That systematization, many, many decades later, starting in the 1970s, led to the automation of the way that we build things. Systematization, then automation. That now allows us to build lots and lots and lots of things very, very cheaply, which is nice in some ways and not so nice, like, for example, microplastics in other ways. Again, we can argue the pros and cons, but from an economic point of view, if we want a large number of things, we as a whole want a large number of things that are affordable to a large number of people, systematization, then automation. Should happen. And it's already happened for the way that we build things indoors, but it hasn't happened out of doors. Why not? As you mentioned, things haven't changed much in the way that we build things outdoors. The photo in the bottom right is from the construction of this building 6 years ago. Why?
The environment's a lot less controlled.
The environment is not controlled, right? The factory was the idea to systematize the way that we build things indoors. Why is the fact that the environment is not controlled, why has that frustrated automation of creation of outdoor infrastructure?
The way that we build and design machines, they perform very, very specific tasks and do that exact task very well. We don't have very good general purpose or adaptable machines.
We don't have general purpose machines, we don't have adaptable machines, we don't have autonomous machines. Absolutely. So over 2,000 years ago, the Greek philosopher Heraclitus said, man never enters the same river twice. You are constantly confronted with change. You've all now sat in classrooms for decades at this point, and maybe it's all becoming a blur. It all seems like the same thing. There's an instructor at the front of the class droning at you. Feels like the same thing over and over again. But if we went in and looked at the photons that were falling on your retina and the pressure waves that were arriving at your ear, it's never the same river twice. You are constantly receiving sensory input that is unique. It's never the same. And yet, you somehow manage to do well in classes. You wouldn't be here if you hadn't. We, as human beings that have had formal education, we're so good at dealing with this environment that it seems like it's the same thing day after day. But if you drill down into what is actually happening to your body and your brain while you think you're in the same river, it's never the same river twice. We do not know how to create machines that handle that fact. We do not know how to make adaptive machines that constantly modulate or alter their behavior to continuously help welding a T-bar that's being, an I-bar that's being put up at a construction site. Very, very tricky to do. These are industrial robots in the upper right. These are these are autonomous machines. Somebody's programmed them to do something. They do it on their own. There's no human with a remote controller. But they're doing exactly the same thing over and over again. And factories have been designed for over 100 years now to make that possible. We cannot do that when we deploy autonomous machines outside. We cannot control the weather, control the wind, control who walks in and out of the robot's work zone. Tricky to do. Yeah? Imagine for a moment we did want to deploy current state-of-the-art autonomous robots out there onto construction sites. They might be programmed to move bricks from pile A to pile B, and their control policy or their brain tells them, go find pile A, choose a brick, drive to pile B, and drop that brick at pile B. Actually doesn't seem that hard, right? You could imagine robots that would be very helpful from an economic perspective that just did that. We program them and train them, find pile A, grab brick, drive to pile B and drop it. Great. We solve that problem in a simulated construction site and then start selling these machines that are bought by construction firms all over the world and deployed at construction sites. What could possibly go wrong? Sounds like a good solution. Why does this hypothetical construction company not exist?
It could be because you're not just building with bricks.
Sorry?
It could be because you're not just building with bricks.
Maybe they're not bricks. Or maybe the bricks are a little bit different size or different shape compared to when the robots were trained to move bricks from pile A to pile B, and they just fail to ever find pile A. They just come back to their charging station and say, I couldn't find any bricks. Okay, kind of a bummer, but not such a huge loss. What else could possibly go wrong? You're going to hear this phrase a lot in this class. We're going to deploy some autonomous machines. What could possibly go wrong? Is that it?
Well, it depends on what method of vision you're using. Like,
Okay.
if you're using a LiDAR, if it's not that precise, and it might try to do object detection and object avoidance by like stopping when there's actually like nothing there, or something really small that it detects as a point and it stops itself, so if it's not precise enough.
Could be, right? So you get false positives. It
Yeah.
thinks it sees like obstacles or things in its path and it stops, and you just can't get this machine to actually do things. It's just paranoid all the time. It's frozen with anxiety. I can't find or do what you're asking me to do. Again, a bummer, but not really that bad, not that big a problem in the grand scheme of things. What else could possibly go wrong?
Me.
Yes,
They could ruin things.
they could ruin things. Like what things?
Well, they could hurt people.
Now we're getting somewhere. How could they hurt people on a construction site? They're not interested in people. They're only focused on bricks.
Well, if they're using like power tools and stuff, those are pretty dangerous.
True, okay.
They're still on the job site.
There are power tools on the job site. We'll keep them away from power tools. What else could possibly go wrong?
You see like 3D printers make one minor mistake and then the whole project is like completely destroyed.
Okay,
So you could see a robot misplacing a brick by a couple inches and then the whole thing just falls apart.
could be. So maybe when they're making pile B, they end up just sort of making tower B. And then that's not necessarily so good. That sounds more problematic right at the end. Yep.
Maybe get in the way of other machinery, like they don't have common sense, so awareness of what's going around them.
There's other machines being driven by humans on the site. This robot is programmed to just take bricks from pile A to pile B. What could possibly go wrong? Maybe on a given construction site, there's a road between pile A and pile B. What else could go wrong?
If you move like one of the arms, if you have 6 degrees of freedom, then you move like the biggest one too fast, you could like completely launch the brick the other way.
Absolutely.
You can hit someone with it. Like a lot of times when you build stuff in a physics engine, I feel like it, and then you just deploy it with no controller, it's too fast and everything, it gets crazy.
Absolutely. It's too fast. It gets crazy. For those that haven't worked with physics engines before, you're going to see this firsthand. A student who took this class several years ago actually did this as a final project, move bricks, virtual bricks from pile A to pile B. The solution that the robot came up with, what could possibly go wrong? Yeah? Okay. Why are we spending so much time on this particular point? This is the boogeyman in all of AI and robotics. It's got a lot of different names in different fields. In robotics, it's usually known as perverse instantiation. We train or we evolve a robot to do exactly what we told it to do, move bricks from pile A to pile B. It instantiated the behavior. What's the problem? From the point of view of the robot, it says, I don't understand why all the humans are freaking out. From the human's perspective, often the machines will instantiate the behavior perversely. One way to think about current state-of-the-art AI and robotics is they're like teenagers. They actually will do exactly what you told them to do, but they do it in exactly the way that, in retrospect, you wished they hadn't. Turns out there's lots and lots of ways for machines to do literally what we ask them to do, and 99.9% of those ways are really, really bad for humans. Imagine we built some robot planes that could scoop up water and dump them on the wildfires, and we just left those machines to try and figure out how best to put out the wildfires. I will leave that for you to think about. Okay, so economic reasons for robotics at the moment. Good economic reasons. If we could build infrastructure outside at scale with adaptive robots, that would be a huge economic benefit. Part of the reason, one of the things holding up the deployment of ever larger wind farms and solar farms and tidal farms and wave farms is what? What do you think the limiting factor is? Limiting factor is humans. It's always humans, but how so? How humans?
A human can only work a certain amount of time every day.
A human can only work, yeah. And if you're putting solar panels in the Southwest desert, not great. If you're putting wave farms off the coast of northern Scotland, not great working conditions. Yeah? In all large energy infrastructure projects, the major part of the budget is labor, for good reason. But again, if our goal is to build large-scale infrastructure to wean ourselves off fossil fuels, again, this is my opinion, it would be good to facilitate these workers or possibly replace these human workers with machines. Okay, let's keep going. Third reason you might want to deploy robots, as we just said, is to replace human labor. This was a homemade YouTube video of a farmer who was very proud of this device that they built. Look at how comfortable these workers are. Not to poke fun at this particular farmer. I want you to imagine for a moment, hard to do today, but I want you to try your best to imagine actually being on this device for a 10-hour shift. Why is the farmer so proud of this device?
Without the device, the workers would have to constantly be bending down at the project.
They still have a 10-hour shift, right? Apparently, this is better than the alternative. This is one of the best solutions for manual agriculture. You can probably guess that this is, in the West. Other parts of the world, manual labor, mostly agriculture, agonizing, backbreaking work. Not that it's not valuable work or rewarding work, but if we just think about the physical toll of labor in general for most people on this planet right now, it's not such a fun job. Anyone actually done manual labor for a considerable period of time? Yeah. Okay. Obviously, precision agriculture is a thing. There is a very real movement to deploy robots, and this is one of the economic sectors in which robots are doing pretty well, that actually are replacing human workers. Why? Why is precision agriculture moving ahead faster than robots in other economic sectors?
More profitable?
I don't know if it's more profitable. I'm not an economics prof. It's a good question. It certainly is profitable, but there's other economic sectors like construction and solar panel deployment and maintenance that would also be economically viable.
Farms have a predictable layout.
Farms have a predictable layout. A plot of land in a relatively flat field in the West where there's sufficient sunlight and water, it's actually kind of close to a factory. It's not a perfectly controlled environment, but it's somewhere in between. Yeah? So not surprisingly, if you look at the actual autonomous robots that are out there at the moment, they're actually in what are called semi-structured environments. This is a semi-structured environment. Where else are actual real-world autonomous robots operating at the moment? And what is the associated semi-structured environment? Outside. Factories, robots have been around for 50 years in factories.
On the road?
On the road. Specifically the right-hand lane of highways, specifically in Europe. So there are movements in many countries to make sure it's either the rightmost lane or the leftmost lane, depending on which European country we're talking about, that is for autonomous vehicles only. It's possible that we can take existing transportation networks or certain parts of those networks and make them more controlled environments and deploy machines out there, autonomous machines, that are going to move at very high velocity, relatively close to human-occupied vehicles. Bit of a gamble, it seems like, but we'll see.
Also, like trains or some subways, semi-automated or automated.
Absolutely. Trains and planes. If you fly on a plane these days, there's a human pilot in the cockpit. They're usually watching and not driving. Again, semi-structured environment, at least after takeoff and before landing.
Those little robot guys in big cities that are for deliveries.
The food delivery robots?
They're bad though. Like they get.
Yeah, they're having a hard go.
They
Yeah,
have a hard time.
they're having a hard time. The streets of San Francisco, not quite a semi-structured environment. Not as much as the folks in San Francisco who are deploying these machines would like to think, I think. Okay. All right, so we've seen existential reasons for robots, economic reasons for robots. There's also a scientific or intellectual reason for robotics, which is they actually help us study the nature of intelligence. Right? There's a huge argument that's been going on for a few years now. Is ChatGPT intelligent or not? Does ChatGPT understand or not? Is ChatGPT conscious or not? Does ChatGPT know that it knows or not? Does ChatGPT know that it doesn't know or not? Pick your argument. If you look at any of those arguments, it's interesting how many people are so sure that ChatGPT doesn't understand, like us. There are other people that are so sure that it does. How can there be this fundamental disagreement about understanding, learning, thinking? We all understand, learn, think. You've all been doing it for decades. We should understand what understanding is. It should be obvious whether something is or isn't understanding or learning or thinking, or being conscious. Turns out that if you actually think about any of those nouns and actually try and come up with a definition or a formal definition for any of those things, it's super, super hard. One of the things that I think is fun about robotics and AI is it keeps challenging our preconceptions about ourselves. We are so sure, most of us, are so sure that we understand, we think, we feel, we love, we hate, we are conscious, we know that we're conscious. We're so sure of all these things. One of the things robotics and AI is showing us is that maybe we're not as sure about what these cognitive phenomena is as we think. Another annoying phrase that I'm going to say many times in this class, apologies in advance, thinking about thinking is misleading. If you introspect, you watch yourself thinking, understanding, you watch yourself listening to the words I'm saying right now, it may seem obvious to you that you're doing it, you're understanding. Are you? What does that actually mean? It seems, from my view at least, that this is an open frontier in science. The actual understanding of cognition, full stop, thinking, feeling, understanding, consciousness, it's vague. We don't have a good grasp on what these things are or whether they even are things. There's a branch of philosophy that's called illusionism, which is that you think you have free will and you think you're conscious and all the rest. It's all an illusion. You don't. Kind of scary for some people, but also hopefully it gives you pause for thought. These things that you have, they're there. You have a front row seat for all of these cognitive phenomena because you can do them. And yet, as a society, we don't understand them very well. At least we don't have a good scientific understanding for them. So there is no guiding theory in intelligence. If we really understood what intelligence is, we should be able to sit down and make machines that are intelligent. The fact that we're having such a hard time doing so, in my opinion, is an indicator that we don't understand scientifically what intelligence is. We have no guiding principle to guide us. All other branches of science have a guiding principle. Biology has descent with modification, otherwise known as evolution. Physics has Newtonian and quantum mechanics. There's still many interesting open questions in biology and physics, but the answering of those questions is usually guided by these underlying frameworks. What's the guiding theory or principle in chemistry? Biology has evolution, physics has Newtonian and quantum mechanics. What does chemistry have? When you took chem for the first time in high school, what's the first thing you're taught? The periodic table. Turns out that there's some interesting underlying structure between all the elements that we've found so far in the universe. Interesting. There's a guiding principle. What's the guiding principle for intelligence? Hopefully, robotics and AI will help us develop one. One of the other scientific rationales, I would say, for robotics and AI is that it's the most interdisciplinary area of study. In this course, we're going to dip into evolutionary biology, neuroscience, cognitive science. In fact, we've already dipped into these topics. Psychology, biomechanics, the nature of movement, physics. You're going to be building a physics engine in this class. You're going to do a lot of coding in this class. We're going to look at a lot of physical robots in this class, which involve mechanical, electrical, and sometimes bioengineering. We just talked about chemistry. We'll see chemistry again when we talk about soft robots. A lot of math goes into robotics and AI. And then again, all of these technologies, or the pursuit of these technologies, often point us back at ourselves. If we think ChatGPT is really not understanding, and we are so sure that we understand, what actually is the difference? We're going to stop here for today. I will assign you a quiz on Brightspace that is due at 11:59 p.m. tonight. Please start in on assignments 1 and/or 2, and I'll see you back here Thursday morning. Thank you.